For today's video, we are going to be following along with an Unsloth AI instruction that essentially allows us to train our own reasoning model akin to what DeepSeek was capable of doing. And this example is actually going to touch upon some of the specific things that were found in the DeepSeek research paper where they had the quote-unquote aha moment with R1 However, we are also going to look at how this whole concept of kind of reinforcement learning that ties into what we do today has actually existed for perhaps a bit longer than we may have actually realized. Now, before we get into it, I have had folks ask me to actually just specifically list the hardware that I'm using for these videos, so I am going to begin doing that now. I apologize if that has been vague up until this point. I will just put it in a little box on the screen so that you can kind of read and see what's being used for any one specific video. Now, with that out of the way, we are basically just going to hop into it here. The actual example here in this blog post by Unsloth AI is actually from only a few days ago, so February 6th, and today is February 11th, so fairly recent. However, this is actually designed to be used in a Google Colab notebook. Now, I'm not the biggest fan of notebooks. However, I can't help but admit that for educational purposes and things like this, where being able to see execution kind of cell by cell can help understanding, they are pretty good. However, we are actually going to be doing this locally, but maintaining the notebook format. So we will actually be using VSCode with this, just with the Jupyter Notebook extension. And we will get into kind of more of that and the requirements as we progress through the video. However, let's just kind of take a look at this article right here and just go over more of a surface level of what's actually going to be happening today. So we can see that we are going to be playing with some reasoning in Unsloth. DeepSeek R1's research realized an aha moment where R1 autonomously learned to allocate more thinking time without human feedback by using GRPO, or Group Relative Policy Optimization, which may sound a bit complex and verbose. However, fortunately, this is more of a surface level overview, and we'll actually get to hands-on play with this, so being able to see it is definitely helpful in terms of being able to understand, I find. If we scroll down here to the main details and things of that sort, well, first we can see that the talented individuals at Unsloth have enhanced the entire process, making it use 80% less VRAM, and essentially this allows us to reproduce R1's aha moment on just 7 gigs of video RAM using Qwen 2.5, which is here in parentheses the 1.5 billion parameter variant of that. For today's video, we are actually going to be using a 3 billion parameter variant of Qwen 2.5, which we can see linked right here, but we won't get ahead of ourselves just quite yet. In the main details here, we can see that this allows us to transform any model up to 15 billion parameters into a reasoning model, and my assumption is if you had more than this VRAM available, you could go higher than 15 billion parameters. We can see there's a bit more here previously, and this is kind of where this becomes very cool implementation wise and kind of what allows us to actually replicate this on perhaps consumer hardware. Previously, GRPO was only supported for full fine tuning, but they have made it work with QLoRa and LoRa. Now, you may have heard LoRa thrown around, but perhaps just kind of you've heard it, but you don't quite understand it. Now, it is not my intention to really give a technical deep dive into it, but I think it would be helpful to just kind of touch upon what that actually is and how this allows it to be so much more efficient than full fine tuning. So if we go into this GitHub here for LoRa, we can actually see, and you don't actually need to follow along with this. This is just kind of a demonstration thing. So don't feel like you have to type in GitHub LoRa or anything like that. We can see that LoRa is a low rank adaptation of large language models, and it reduces the number of trainable parameters by learning pairs of rank decomposition matrices while freezing the original weights. Ignore like the complex technical sounding terminology here, but basically it reduces the number of trainable parameters by freezing the original weights. So basically this reduces the storage requirement for LLMs adapted to specific tasks and enables efficient task switching during deployment, and then it gets a little more kind of like technically here. But basically, if we scroll down here, we can see that there is an example here with a specific version of GPT-2 where we can see if we were to fine tune this model to actually kind of modify it to our use case, the number of trainable parameters would be somewhere around 355 million. However, with the application of LoRA, I suppose that's probably not the correct terminology, but by applying LoRA to the model instead of fine tuning, we can see that the number of trainable parameters drops to 0.35 million. So from 355 million trainable parameters to 0.35 million, which is a gigantic reduction in, I suppose you could say, computational expensiveness of actually being able to modify this model. Now, there are tons of resources out there for better understanding this and things like that, but I did want to just kind of give a little bit of pertinent background info of what this actually means when we see it right here, that they have supported it now for QLoRa and LoRa. So to continue on now, and hopefully that wasn't kind of too lacking or verbose, we can see that this is different than fine-tuning DeepSeek R1 distilled models. This is converting a standard model into a full-fledged reasoning model using GRPO. And again, this is really educationally valuable because we actually get to go through the steps here, and not only do we see it like working, but we actually get to compare the final result using the original model and then the one that we actually converted into a reasoning model. And it is really cool. If we scroll down here, we can see there's a bit more kind of technical information along with an example of what we will actually see, where here's the answer before and then here's the answer after, where basically the model now has a reasoning chain and capability. We can see that this is kind of stemming from reinforcement learning. So DeepSeek's researchers observed the aha moment with pure reinforcement learning. And I do want to quickly just mention this as more of like maybe historical pertinent information, if nothing more. The whole concept of reinforcement learning has been around perhaps longer than you may realize. And if we go over here to this PyTorch example, we can see that this is actually an example of reinforcement learning and a tutorial that was posted on 2017, on March 24th, 2017. So a while ago and long before things like ChatGPT and things like that. Okay, it was updated recently, but it was created in 2017, and we can see here that basically through this example, which we're not going to do, I just kind of wanted to share it because it may be somewhat kind of relatable. Basically, an agent learns to keep the pole standing up by deciding whether to move the cart left or right, and it kind of learns that through the concept of reinforcement learning. And we can see that the paper that this actually references here was published in 2013. So it is just cool to be able to see the way that some of these things build upon older discoveries and things like that to actually propel new advancements and things of that sort. Now, with that out of the way, we can just basically scroll down a little more, and we're really kind of essentially ready to actually go ahead and just start playing with this. So there's a few other things down here, but we will actually see some of this happen when we go ahead and actually run the example. As I'm watching the video back real quick and editing, I realized that I want to actually show one other thing in here before we jump into it. And that is really just a quick overview of how GRPO actually works in this scope. So if we scroll down here below the aha moment where we can see the comparison with 5.4, we really do see a very simple layout of how it works. So 1, the model generates groups of responses. 2, each response is scored based on correctness or another metric created by some set reward function rather than an LLM reward model. 3, the average score of the group is computed. 4, each response's score is compared to the group average. And then 5, the model is reinforced to favor higher scoring responses, which is kind of what steers the model to behave in the way that we would like it to. So we can basically see that there's some more here about that, but I did just want to kind of go over this simple 5-step how it works, because I didn't want to just jump straight into the video without giving a clear kind of look at what we're actually going to be doing with the model that we are now going to go ahead and actually train. So with that, I'm going to just throw this back into the normal video as it was filmed, and yeah. So with that said, we are really going to go ahead and actually just pop into this. Now, we can see that if we want to just click on the actual notebook, we can click this link right here to try it for free on Google Colab with Llama 3.1. If you do have a Google account, you can connect to a free T4 instance to actually run this on the cloud, if you will. However, because I like local, and I'm sure a lot of folks watching like local as well, we are going to basically follow the steps to do this locally. So to actually get started and now go ahead and run this ourselves, we are basically just going to go ahead and click on the link right here for GRPO notebooks featuring other models, and there is a docs link. So if we click on this, we can see that we are now met with a few different options. For the purpose of this video and to keep things a little lighter and more simpler, I am going to opt to use Qwen 2.53b. So I will just click on this and it will open the actual Google Colab notebook for Qwen 2.53b along with this Unsloth example. Now, being that this is going to be done locally on our own machine, we are going to simply download this, and really it is quite simple. We just navigate up here and click on File, and from there we go down to Download, and from the two options here we click download.ipynb, which is just kind of the notebook file. And you can see I've done this a few times now, as I have actually been playing with this for a few days myself, as I think it really is quite interesting. So following that, we are going to open up VS Code. Now, for the purpose of this video, I'm not going to do a section on installing VS Code, as I think it's pretty widely documented and it is quite simple. But when we do have VS Code open, we are actually going to want to add in the notebook extension. And in order to do that, we can just navigate over here to this button, which is the extensions, and it will open the extensions pane. And we are simply going to search for Jupyter. And we will see that this pops up right here. And in order to install it, we can just quite simply click this install button and it will go ahead and install it into our VS Code as an extension, if you will. And we now have that all set. So we can basically just go ahead and click this button again to close the extensions pane, and we can also close this. So now we are going to basically just go ahead and actually open the downloaded notebook file, which for me is in my downloads location. So I will just click open there, and we can see that, okay, so this opened in a messy spot. If we scroll all the way up, we can see that this is essentially the exact same thing we saw online in the Google Colab instance, except this is now on our local machine and almost ready to be used with our own GPUs. Now, before we do this, there are a few dependencies that we are going to need to install in order to get this to run on our local system. Personally, I like to opt for Conda environments when I run these examples because it keeps everything kind of contained to prevent perhaps issues and mismatches and things like that. So the next step is going to be to create a new Conda environment, which I will do right now. And you can name it whatever you want. I just named it Qwen RL for Qwen Reinforcement Learning, I suppose you could say. And once the environment has been created, we can just activate it. Sorry again if my mouse work is kind of messy. I'm using what I honestly think is like the world's cheapest wireless mouse, so it's really kind of like glitchy often. Now, we don't actually want to run this cell right here as is to try to install the dependencies, but from here we do get a little bit of an understanding of what we actually need on our system. So fortunately, I have just also put these into a text file that I can simply copy paste because there are a few more things that we need. I am going to just copy this and paste it into the terminal right here. So the packages we are going to need to install are as follows: VLLM, Unsloth, diffusers, pillow, IPy kernel, and IPy widgets. So basically, we just type all those in at the same time and press enter. Now, if you are doing this for the first time, it may take a little bit longer. However, as I've run through this example a few times, they are cached on my system, so the actual kind of process will perhaps go a bit quicker. And once this is actually finished, we will see that there is one other thing we need to install, and that is the specific TRL nightly version. Now, If you are not familiar with TRL, basically we can click right here and see that this is the Transformer Reinforcement Learning Library from Hugging Face, which is a full stack library where we provide a set of tools to train transformer language models with reinforcement learning. And for those of us who actually want a bit more of a deep dive on the actual kind of way we're going to be turning this model into a reasoning model, we can see that GRPO is actually listed here in the documentation on Hugging Face. And this basically gives us a more technical and in-depth look at perhaps how this kind of works. There's some charts, there's some math behind it, and things like that. And we can also see we have these logged metrics, which we will actually become more familiar with as we actually get into training this model and things like that. So if you just scroll down here, you can see there's a lot of pertinent information about this specific methodology and many others in the Hugging Face Transformer Reinforcement Learning Library. And basically, we can see that the installation of all of these things has been completed. So we will just hop back into VS Code and ensure that we actually run this command right here as well, which will install the specific version of TRL, which of course we just kind of took a look at. And again, it is cached on my system, so it will go a bit quicker. But now that that's done, we are one step closer to actually being able to run this. Now in VS Code, if you are using a Conda environment like this, you are going to want a way to actually ensure that the VS Code instance can actually communicate with that Conda environment, because the Conda environment is where all of the required dependencies are. So to change into that environment, again, this may be slightly different depending on system version, things like that. But generally, you could just click right up here and you will see that this is actually a button you can click on. So we are going to click on this, and from there, it will open a little drop down right here. We are going to click select another kernel and then Python environments. And from there, it will actually give us the option to select the new Conda environment that we had just created containing all of the requirements, which for us, we have named QuenRL. So we are going to click on that right here. And we are now this is linked to the environment with the dependencies that are required to actually run this. So now we're actually really ready to go ahead and start sequentially running through these cells. Of course, we are going to forego running the installation one, as we kind of handled the necessary packages and Conda environment separately, but we are going to start by going ahead and navigating to this Unsloth one right here. Now, when we run this cell, we can just kind of think of this as applying some like Unsloth magic and optimizations and things like that that will kind of just allow this to work and make it work quickly, I suppose you could say. Now, to run this cell, we can just hit the play button right here to actually execute the cell. And if we do this, we will see that we get a little timer here and some execution output right here. And assuming everything was set up all right, we won't get any errors, and we will see a check mark next to it along with the total time it took to execute the cell, which was 3.6 seconds. Following that, we can just kind of move on down sequentially to the next part, which is actually to load up Qwen 2.5 3B instruct and set the parameters. Now, to be honest with you, before we go further, I am actually going to restart my system because I need to change the fan curve. It is running to actually run the fans high because the graphics card will get too hot if I don't do that. So you won't need to do this, but I will need to go ahead and take a break real quick to restart the system before we run this cell. All right, I don't know how loud those fans will show up kind of through the microphone, so I apologize if it is a bit louder, but I do need them running full speed for what we're going to do here. So the next step here is to load up Qwen 2.5 3B instruct and set the parameters. Now, this isn't going to be a like technical in-depth thing here, but we can just see that we are loading the model here, and we can see that there are some kind of LoRA applications going on here, like the kind of layers they'll be applied to, if you will, and things of that sort. So we are going to just go ahead and execute the cell, and we will see right here that this will actually go ahead and spike GPU utilization, as this is essentially loading the LLM into VRAM. So we can see that it is now using around 11 to 12 gigabytes on the card once this has finished loading. And if we scroll down here to the actual output below the cell, we can see that it has correctly identified the GPU we're using, the maximum available video memory, Torch version, CUDA Toolkit version, and things of that sort. So we'll let this run for a while. We can see this took around 30 seconds, and we are now using around 12.5 gigabytes of video RAM. The 7 gigabyte figure that we saw in the actual Unsloth blog post pertaining to this was if we were using the 1.5 billion parameter of Qwen 2.5. So based on what I see here, I suppose that kind of does track as similar. So if we scroll down, we are going to see a data prep section. And as much as I just want to like click execute cell here and just roll through it till we can see this training, basically what this does is it kind of generates the expected response output we want the model to actually give, which of course we can see here is like reasoning and then answer and things like that. And in addition to that, it actually also does kind of define some of the rewards that the model will be given depending on some of its response metrics, I suppose you could say. And again, this is far more surface level than what's really going on here, but these are things where basically you could go ahead and actually like paste this into an LLM and ask it, like, in the context of reinforcement learning and GRPO, like, can you tell me about how these rewards work to actually modify like the model's behavior, or things like that. And that would actually be a good way to get a more deep dive in without needing to know too much background info. So we are just going to now execute the cell right here, and we will see this one happens quite quickly in 0.9 seconds. So the next thing we're going to do is set up the GRPO trainer and all configurations. And we can see here that this is kind of a bunch of more like technical jargon. We can see that you may have heard of like the AtomW optimizer in terms of training machine learning models and things like that, but this is all kind of mathy, if you will. So I think basically we're going to just skip through going through this step by step and just saying like this is going to set up the training configurations for the model and things like that. So we can go ahead and execute the cell, which will happen near instantaneously, to the point where you may actually be confused, like, did something go wrong or was it supposed to be that fast? And it was, because this is just kind of setting up some training parameters, which happens very quickly. So following this, we are going to scroll down and we will see that there is kind of a sample here of a table that we will begin to see when we actually begin training this model, which we would do right here. Now, without getting too technical, I believe it would be somewhat pertinent to actually just have a bit of an understanding of what we're actually going to see here. And quickly before that, we will see that this is going to go on for 250 steps. So basically, when this number reaches 250, this training will be concluded. Basically, for a more technical explanation of some of these metrics, we can see that in the Hugging Face TRL under GRPO, these are actually kind of listed here as well. However, without having to get into like this stuff, which is confusing, we can basically minimize that and say, okay, so the training loss, just think of as like how well the model's doing in its task, I suppose you could say. Again, non-technical, but kind of what it is. Reward is basically, if the reward number is going up, it means that the model is doing a better job actually kind of adhering to what we want it to based on this data prep section and things like that. So as the reward goes up, it means the model is doing better, and we can see we'll probably get no reward for the first 100 steps. The goal is to see the reward column increase, which basically for what we're doing here means the model is actually starting to do a good job. Reward underscore STD is like the standard deviation of the response groups and their rewards. So basically, when the model is actually being trained here, it is going to generate 8 different responses for each question it sees, and each one of those will be given a reward. So reward standard deviation is basically how much the reward of each one of those individual responses kind of varies comparatively to that group of 8 responses. So hopefully that makes sense, but it's almost like how widely varying the reward for each batch of responses is. And a batch of response would be the 8 responses that we get per like a training step, I suppose you could say. Completion length, just think of it's like how much text it's outputting, I suppose you could say. And then KL is it's loss divergence, I believe it says here. So no, the average KL divergence between the model and the reference model calculated on completions. So to more simply kind of explain this, I suppose we could say that is essentially how the model is responding. We basically don't want the model to go crazy and not behave like itself whatsoever. So the KL divergence kind of compares the model's output to what it would have expected it to be outputted based on the reference policy right here. So basically, we want to make sure that the model doesn't lose its grounding or kind of personality while it is learning to actually generate the reasoning and chain of thought sort of things. So just think of this as like, I don't want to say how lucid the model is, but this is how well the model is still staying grounded in its responses, so it doesn't start just making up gibberish and totally going off the rails in its responses. Again, this is more of a high-level unscientific overview of what these are. And again, I say unscientific, so when I make a mistake, it's just plausible deniability, and I'll be like, oh no, I was unscientific, so I didn't mean to be fully correct. I'm kind of kidding there, kind of. So with that out of the way, we can actually go ahead and begin to start training this. And all we're going to do here is click execute cell. Now this will actually take a little bit of time. I do recall somewhere here I saw that there was a kind of time estimation. However, I do not really remember where I saw that. So doing this is going to take probably about 30 to 40 minutes on my machine right here, utilizing one 3090 Ti. I am not going to sit in front of the camera here for the entire run of the training. However, I will screen record it and we will basically see this going. This is going to very heavily utilize the graphics card in both power draw and the GPU kind of metric right here, which is 100% utilization. And we can see that the video RAM has jumped up a lot, as well as the power consumption, which is around 350 out of 450 watts. So we'll see the temperature go up, obviously, which is why I have the fans going at 100% to keep that. I don't think that should go over 46 Celsius throughout the run, so hopefully we'll see. And we can basically see that the model is kind of just like doing its thing. So output is truncated, but we would like to see more of it. So I would like to view it as a scrollable element. There we go. And then the actual table here starts to become populated for each step of the training, of which there will be 250 of. And then we can also see like some things here. This is partially why I don't like notebooks, because they can get a little visually overloading, I suppose you could say. But we can see like kind of what's going on here as this trains, and it is really kind of cool. And again, this will become quite clear once we actually finish training and do the one-to-one comparison on the newly trained model's response to a question versus the untrained original model. So I am basically going to go ahead and kind of just let this run, and we can see that these tables are becoming filled and the values are changing depending on which step we're on. So we're basically going to just leave this as is for the duration of time, which seems here will take around 27-30 minutes. So, all right. So we can see that we just hit step 250, which essentially means that the training has concluded, and we can see that is true because the GPU utilization has dropped to 0 and the power utilization has dropped massively as well. So if we kind of go through this chart, and I will have time-lapsed over this at a specified speed, which I don't yet know, but we can see that the numbers obviously changed per step and things of that sort. Now, when doing this, I do believe it is said somewhere, maybe not here, but that this is a very, very low amount of steps to have trained the model with. So we can't necessarily expect perfect performance. However, instead of, I suppose you could say, wasting time just trying to analyze the differences in steps and things like that, really the best way to actually show what has gone on here is to just continue scrolling down and try the inference example here in the notebook. So basically, we can now try the model without the GRPO training that we just did. And if we do this, we are going to basically just send it the prompt, how many how many R's are in strawberry, which is obviously a common question given to LLMs to kind of test them and trip them up. So we can execute this cell now here, and it will basically ask this model. So we can see that it said there are no letters R in the word strawberry. Let me just try that again. There are 2 R's in the word strawberry. So each time you execute this is asking it basically again. So we can see it's kind of cycling through. So now we are going to try it with the LoRA that we just trained with GRPO. We need to first save the LoRA. So we are just going to press this right here, which will go ahead and perform that save. And now we are going to load in the LoRA and test, and we can see that this test here is actually slightly different than the one here because we are kind of giving it the system prompt and things like that, which we can kind of, if we circle back up all the way, this is partially why I don't like notebooks, is they can get messy. But if we circle up here, we can see like that system prompt being specified here in the data preparation step. So if we scroll on back down to the inference example with the LoRA loaded, we can press right here and we will press play. Now I want to say we didn't train this very long, so it is very likely that it will still incorrectly count the number of R's in strawberry, but for the purpose of this whole example, we're not as worried with what it says, but more about how it says it. So check this out. Comparing it to this, which is there are 2 R's in the word strawberry. That was its response prior to this. And now after it, we will see that it has a reasoning token, or not a reasoning token, but a reasoning tag right here. To determine the number of R's in the word strawberry, I will count each occurrence of the letter R within the word. The first R is at position 1, the second R is at position 5, the third R is at position 6. Thus, there are 3 occurrences for the letter R in the word strawberry. It actually answered it, and it did do the reasoning tags and things like that. So the whole exciting and cool thing about this, sorry if I'm getting a little loud. 1, I'm excited, and 2, those damn fans are really quite loud. But we just basically made a reasoning model using this. This is a model that, as we just saw prior to everything we did right here, did not have that reasoning capability. Its responses were similar to a normal kind of old school LLM where it basically just gives you the answer right there. But now with this appended and actually tested after our training, when we play this, we actually get a reasoning and chain of thought output, which is so darn cool in my opinion. And we just did this all with this tiny model. It is, of course, technical and things like that and can be a little difficult, but when it comes down to it, it is quite easy to actually just kind of follow along with this and be able to ultimately visually see the difference in what happened here, which is this model that otherwise did not, I'm probably repeating myself, but this is so cool, and I think it's just such a fantastic learning experience. This model, which otherwise would not have had this reasoning chain of thought capability, is now able to actually think and answer based on that. So basically, for the purpose of this video, there is some more in the notebook here, but we're not really going to go ahead and actually play with any of those because they're kind of outside the scope of what we wanted to do here, which is actually just be able to play with this model. And if you want to, you can actually go into the cell and change the question. So what is a beefy, and again, this might kind of trip it up a little, but let's just go ahead and ask it and kind of see what it says. A beefy GPU, short for graphics processing unit, refers to a powerful GPU. The term beefy is used to describe a GPU that is highly capable, fast. Okay. All right, so. Okay, and again, it kind of just gave us an answer and didn't really give us a chain of thought, but this is trained on like a way that it's best if it just answers like mathematical questions or things like how many R's are in a strawberry. So if we go back and run that again, we will see that we have our reasoning kind of capability. Really, this is probably going to conclude this. I do want to just pop back up here real quick. Again, thanks to the very intelligent folks at Unsloth here for actually kind of providing this example and these notebooks and things like that. And we can see everything we have just done leads us to right here, or this aha moment, where basically we see the before and after with the model that we actually trained ourselves on our own local machine, which really is quite awesome. So overall, this is technical depending on how deep you want to go into it. Some of the things I shared earlier in the video are definitely pertinent for those who want to do more perhaps scientific reading, like the TRL library page on Hugging Face, specifically about GRPO. You can look into the GitHub LoRA to see like a example of what it is and how it works and things like that, among many other kind of educational resources online for all these things. But I wanted to just kind of do an overview video where we ran through it together on a local machine to actually be able to do this. It is really cool. And again, I think the educational value of being able to hands-on play with this stuff and do it on your own machine is quite immense. So that is really going to conclude this video. I am now excited to turn those fans down as they are quite annoying. And really, if you have any questions, leave them in the comments or just Google them if there are any scientific related questions. But if you have any questions, just leave them in the comments, and thanks for watching. That's going to conclude it.